Hello students. So next topic which we are going to get is the completion of the forced harmonic oscillator. In the morning we have seen that the forced harmonic oscillator, the equation of the forced harmonic oscillator, we have derived it out. So that equation was being derived by using this particular equation of 4 parameters. So then we have done the solution of all this, and we got the value of amplitude is equal to f naught by m omega naught square minus omega square plus 2 eta gamma omega, and that this was the factor. And then we have to further simplify it out, and this we have got the component of a cos phi and a naught sin phi of this form. And then finally we have calculated about the f is equal to f naught by m of this factor, and this tan phi has come out to be under root of 2 gamma omega naught square minus omega square. So this was, we have find it out. Then we have write this expression in the form of mechanical impedance, which was equal to f naught by omega zm, where zm is equal to under root of a square plus k by m minus m omega whole square, and which factors for high frequency or low frequency we can able to dominate it out and got the respective values. Now we are going to draw the amplitude response curve for this one. So this is the amplitude frequency response for a forced harmonic oscillator. So in that case we have seen there are three different kind of curves: zero damping, low damping, and very high damping. At very high damping, the means at very high frequency the oscillator works at very poorly. At low damping it works intermediately, and at zero damping it works very smoothly or very high, extremely well value for this one. So this is the amplitude for amplitude graph for frequency for this high frequency oscillator. So this shows that dependence of amplitude on frequency is called as amplitude frequency curve, and the curve shows that the amplitude become maximum when omega is nearly equal to the natural frequency. So as soon as this value is coming to the natural frequency, this is the point of natural frequency, and when it becomes natural frequency, so the graph is going to become maximum. So this is frequency at natural frequency is called as the resonance frequency. So this resonance frequency, we are going to get it out, and as soon as we move away from it, its sharpness goes on decreasing. Now we are going to get the values of wave equation for low frequency, for high frequency, and at resonance. What will be the kind of equations we are going to get it out. Now this is the first case when we have the low damping, when the omega is very less than the actual frequency. So in that case, the amplitude we have find it out, f naught is a naught is equal to f naught by omega into zm. Now zm was equal to under root of a square plus k by omega minus m omega whole square. When omega is very small, so that means this value will be very larger. So that means zm will be equal to, and which will be very large as compared to the one, it will be equal to under root of k by omega. So when you put this value over here, so it will be a f naught upon omega into k by omega. So this will be cancelled, that is equal to f naught upon k. So that means this amplitude will come out to be equal to f naught by k at very low frequency. So this is the equation which we are going to get it out. So this equation shows that that the external driving force acts as a constant static force which pushes the particle to a maximum distance, that the force balance. So that means f naught is equal to which is equal to x maximum into k, or x maximum is equal to f naught upon k. So that means the amplitude a naught is equal to x maximum, that is the maximum distance up to which it can go when the frequency is very large. So that means at low damping, low driving frequency, so this is the value which we are going to get it out. Now we can find the value of acceleration as well as for the displacement. Now since acceleration depend upon the square of the frequency and displacement depend upon this one, so we can find it out that when the value is very small, both accelerations and this value will be negligible small, and this equation of motion reduces to, so what we can get is, So this equation of motion reduces to omega naught square y is equal to f naught by m cos omega t, or we can get f is equal to f naught by m omega naught square into cos of omega t, and that the value, or m omega naught square is k, so that means f naught by k cos of omega t. So that means at low frequency the value of y comes out to be f naught by k cos of omega t. So that is the equation for the low driving frequency, when the frequency of driving frequencies source is very small. Now that means at low frequency the circuit cannot be driven properly. It can go up to small value of displacement. Next is the case 2, when omega is much larger than omega naught. So what will happen when omega is much larger than, so this value will be very small, so only this factor will dominate. So Zm is equal to m into omega only. So that means f a naught will be equal to f naught by omega into m omega, that is equal to f naught by m omega square. So that means at very high frequency, so the amplitude will be equal to this one. Amplitude decreases with the frequency in high frequency region, so that means if the frequency is very high, amplitude will be very small. So at high frequency these two factors will be very small, elastic factors and the driving frequencies. So this motion is determined by the external driving frequency. So that means y is equal to f naught by m cos of omega t, and sorry, that is d2y by dt square, and y will be equal to minus f naught by m omega square cos of omega t, which is equal to a naught cos of omega t, and where a naught is equal to this one. So external force control as if there is neither elastic or neither damping forces. So at high frequency elastic and damping forces dominate zero, so that means the amplitude will be forced by only the external force, that is the external force which you are applying from the outside source, that is at the high frequency. Now, what will happen at the resonance? Resonance happens when the natural frequency, we are forcing the material to vibrate with the frequency equal to its actual frequency. With what particle, the particles are going to vibrate. For example, glass is plane, is the particles are vibrating. If a plane passes very close to it, and if the frequency of the radiation frequency of the vibration of the plane matches with the frequency of the particles of the glass plane, so it will breaks. So that means that is a resonance. Resonance means the frequency equal to the natural frequency of the glass particles frequency. So this is the case here. So when omega is equal to omega naught, that means the forced frequency is equal to the natural frequency. So in that case, what will happen? So the value of amplitude will be equal to f naught by m. So this will be equal to so this will be equal to f naught by m upon root of omega naught square minus omega square plus 4 omega square gamma square. Now we can get it in the standard form. What is run? Minus 2 gamma square has been the square of this has been added here and 2 subtracted from here. So that means we can get this in the standard form. So this will be maximum when this is equal to 0, because this value has to be emitted out. So this value will be 0 when omega r is equal to omega naught square minus 2 gamma square. So that is the resonant frequencies. So this will be the relation for the resonance, and what will happen at the resonance. So the maximum value of the amplitude, again we can get it is about this one. So that is equal to f naught by m 2 gamma omega naught square minus gamma square. If gamma square is much lesser than omega naught square, so a maximum value is equal to f naught by 2 m gamma omega naught. So that is what happens at the what happens at the resonance. Next is about the quality factor. So quality factor, which this measurement of the damping of the oscillator. Larger the value of Q, larger is the damping, lesser is the damping. In case of forced oscillator, we will see the behavior of resonance changes with the Q of the oscillator. Means if the value of Q changes, the resonance will be changed out. So we know that Q is equal to half of omega naught into 2 or omega naught by 2 gamma. So we can find the amplitude in terms of Q in this form, as well as the phase can also be written in the form of this value of q. So that is by substituting the value of q as this one. So the original equation was this one, 4 gamma square omega square. So what we have got is omega gamma is equal to q into 2 by omega naught. So this value of gamma we have substituted here. That means 4 gamma square 4 omega square into that is this one into 4 q square upon omega naught square. So what we will get is 4 get cancelled. So 4, so that means it is equal to omega. So that means no. Now we are going to discuss this phase curve. Phase curve is drawn between the phase as well as the frequency. So there are two kind of graphs. One is for low damping as well as other is for high damping. And then there is a zero damping. So that is this graph, zero damping. So these are the three different graphs are being drawn. That is drawn from this particular equation. Now when omega is lesser than omega naught. So what will happen? So that means at low frequency phi is very small and positive, which means that placement lags behind the force by a very small amount. So as omega increases, the phase lag of displacement also increases. So that means at low frequency, so this kind of simpler zero value graph is there for this kind of straight line is there. Now when omega is equal to omega naught, when omega is equal to omega naught, so this value, so you will put out tan phi is equal to infinity. So that means phi is equal to 90 degree. So you will get this kind of curve, and then it will be this straight line. Now when this means when the force attain its maximum value, the displacement is zero and vice versa. So that is the particular part. Now the third case is when omega is much greater than omega naught. When the frequency is very large, so that case the graph will be behaving like a heavy damping. So in damping it will be straight line, and then it will be a curvilinear curve for the heavy damping, because when it is very larger, so you will get the tan phi will approaches toward minus zero, where phi is equal to approximately equal to pi. So at high frequencies displacement is I degree out of phase with the force. So due to that reason, so we will get this kind of graph for the high damping. So this was all about the high frequency oscillator.